Alrighty, this is going on page 22. When we're done, we'll explain that before, once we get there to put it in. Before we even start about this, above that little line there, we're going to do a little quick review here. And you probably need to write this stuff down just to be safe. All right, if I have a line that looks like this, is the slope of that line positive or negative? Positive. Okay, good. I'm hoping that these are really easy questions. So the slope of this line is what? Negative. Okay, good. Now, this line, is this 0 or undefined? Sure about that? I forget every time. Okay, you are not the only one. Thank you for being honest. And nobody, the undefined people were confident. You were wrong, I'm sorry. But look, if they said undefined with confidence and you were like, I really thought it was 0, it's okay to say 0. If I don't know where your confusion is, I can't help you. You with me on that? If I ask you a question and you're too terrified to say anything, I don't know what you're thinking. Maybe you're a genius and you know it all. Maybe you know nothing. I don't know. But if you answer a question and it's wrong and I can figure out why you think it's that, I can help you a whole lot better. You with me on that? Now, I know y'all get these mixed up, okay? But we can't get them mixed up anymore, and I'm going to give you a couple of tools for this. So this is 0, which means this one is what? Undefined. Okay. So let's think about an actual slope. Like I'm walking on this floor, right? It's not sloped at all. If I come up to a ramp and I'm going to go up into something, I have a positive slope and I'm going up, right? But right now, I have 0 slope. The slope is 0 and then it would get bigger, right? If I have this, it's not even defined. I can't even walk on it. There's literally, it is not that it's nothing, because nothing and 0, like, that's where we get a little weird about that. Undefined and 0, clearly not the same thing. This slope is not even defined. It's nothing I can walk on or anything else. This slope is defined. It just isn't slopey. You with me on that? The other thing that y'all get mixed up is which one is an x equals line and which one is a y equals line. Those are the easiest graphs to identify, the easiest equations to write, and the most messed up, okay? So I'm going to give you a couple of different ways to look at things. So I want you, first of all, is this one horizontal or vertical? Horizontal, so we can't get that stuff mixed up, right? All right, so I'm going to have you write. Now, I realize some of you may have never really learned cursive, but we're going to pretend like we have a cursive little workbook in front of us, and I want you to write a cursive H like you would learn if you actually learned cursive. Okay, just do the best you can. Because that is a horizontal line, right? Miss Ludicky taught me this years and years ago, and I was like, this is brilliant, and I've been using it ever since. Now, take your paper and turn it upside down and tell me what that H now looks like. A Y. Your horizontal line is, once you rotate it around, is a Y equals line. Does that make sense? So horizontal is Y equals 0. Because the slope is 0 and slope, like if I have Y equals X, that's the parent function, right? If my slope is 0, it's Y equals 0x, which is just then Y equals 0. So then undefined, if I have an X, well, if you rotate that around, what's it going to look like? An X, you probably don't even need to turn your paper, right? But if you split it in half like that, well, pretend like that's a dotted line, you get a V for vertical. I don't care how you remember them, but remember them. We cannot afford for you to make these kinds of mistakes anymore, okay? And I know, I understand why it's confusing, the Y equals and X equals, because it's the opposite of the axis. At least I think that's why we get them mixed up sometimes. But those basic things right there, we have got to have down. Should have had down in Algebra 1, but I know that it gets confusing, okay? We all good on all that? Perfect. All right. So you're going to notice, if you just kind of look at these notes, there's not a whole lot of what you probably consider math on here, right? If we're not solving equations or doing something like that, it doesn't seem mathy. We got a lot of words, okay? The AP exam has a lot of words, and you have to write a lot of words. And the concept itself is important, kind of like we talked about with the parent functions. yes, we need to know what the equations are. We need to be able to graph them and do all that stuff, but also just understand the global concept here. And so you'll find that some of this stuff is going to be super easy reminders, but so when that happens, you can't tune me out and be like, oh, I totally know all this, because maybe you do, but the wording has to be a specific way, and sometimes we're not really changing, but improving what that wording is and how we say things. And I know this is kind of a generalization, but again, I've been doing this a long time. One of the things a lot of you will struggle with is transferring what's in your head and what you know and understand to words on the paper, okay? And even sometimes I'll ask you, well, you'll be like, I don't know what to write. And I'll say, okay, well, explain it to me. You say it, it's beautiful. And then you're like, I don't know what to write. Well, you literally write what you just said. And sometimes we have that disconnect. Or saying the right words and not leaving out a specific word. So make sure you're paying attention to all those little nuances there. All right, let's start here. So it says a blank is a mathematical relation. Okay, so let's talk about what a relation is. If we relate one set of data to another set of data, we could have, it's really all of our graphs, all of our equations, all of our tables, all of them. But some of them have a special classification, and you're very good at them, I think. It's a function. So a function is a mathematical relation that maps, okay, weird word, maybe you haven't heard that in this context before, but we'll get to that, maps a set of input values to a set of output values. So a mapping, we are not looking at a globe or anything like that. You map one set of data onto the other. You take some x's, you do some things to them, and then you get a y. So this x is mapped to this y, okay? That's some terminology you need to be familiar with. Not that you necessarily have to use, but you have to understand when you read it, okay? Some of it goes both ways, but this is really more just understanding when you read it what it means. All right, so maps a set of input values to output values such that each input value is mapped to exactly, now this word exactly is very important, exactly one output value. And that's some terminology you've heard before, right? Each input value has exactly one output value. Does every output value have exactly one input value? Yes? No? Do you ever read those kind of words and you think, I totally know what a function is, but these words make my brain hurt? Okay? Because you can write these sentences. I could restructure the sentence where it kind of sounds backwards and you can get lost in that. When that happens and you are trying to make sure that these words are really what you're trying to think, we can always take something that seems wacky and relate it back to something that we are very confident in. Okay? Are y'all pretty confident with the picture of a parabola? Yes? Okay, so that's the one I would use for something like this. So here's our parabola. It doesn't even have to be the parent function, but we'll make this one the parent function. All right. So when we say each input value has exactly one output value, our input values are our x's. We can see that no matter what, every x has just one y, right? Does every output value have exactly one input value? No. Okay, because whatever this y value is, that y value is the same here and here, and it goes with two different x values. You with me on that? So for some functions, yes, that's true, but not all functions. You with me on that? That's why a parabola is a good one to use. If I use a line, it'll be a yes and a yes. But that way you can get the words correct, because these words are hugely important. As it goes on to say, in previous courses, you may have used the vertical line test. I even used those words with you the other day when we were talking about the parent functions. And that's okay. We can still talk about it and use it. However, we use it to determine if a graph is a function or not. However, in AP pre-calculus, we use the statement, each input has exactly one output. That's why it passes the vertical line test, but we have to use the words. One of the FRQs on last year's test, it was explaining actually why it was a one-to-one function. We'll talk about what that is a little bit later, but you couldn't use the words in your explanation vertical line test. I mean, you could use them, but you also had to say each input has exactly one output. Okay? We must connect inputs and outputs. You have to actually say those words and write those words. Okay? And here's kind of the why. The why is not going to make a whole lot of sense until next semester, but at least kind of explain it a little bit. So later in this course, we will learn why the vertical line test is not a valid explanation. So in Unit 3, we discover polar functions, and they often fail the vertical line test, but are actually functions. You don't know what those are yet or what that means, but that's part of why we have to use the words, okay, so that it works for all of the functions that we talk about. Alrighty, so back to something that the concept I think you fully understand. The writing them out sometimes not so much. All right, so we have a set of input values and output values for a function. Input values could be our x. Does it always have to be x? No, it doesn't have to be x, but and the output value doesn't always have to be y. And I couldn't figure out how to ask this question without like giving it away. The set of all x's that we get to use in a function. Anybody tell me what that is called? It's okay. It's because I'm not asking it well without getting. Is it domain or range? Domain. Okay, that's what I was getting at, but I couldn't. Okay, so it is the domain. Again, total old business. And is it represented by the independent or dependent variable? Independent. Okay, and then, oops, got in my E. Set of output is called the what? Range. And it's represented by the dependent variable. And that's total old news too. We're talking, I don't know, it might even be before Algebra 1 that you actually learn that stuff. Again, I think you totally understand the concept. If we start writing down intervals of domain and range, that's where things go off the rails for some people. And I'm not sure why it's that's one of the things I can't figure out, why it's such a difficult concept. When we write and talk about domain, you always go from left to right. When you write and talk about the range, you always go from bottom to top, least to greatest on both, just like on a number line. So be cognizant of that. All right, so now let's talk about positive and negative. And we're talking about the function. And you'll understand when we get to the back why I'm making such a big deal about it's the function. When the function is positive, f lies above the x-axis. So that means the outputs or the y values are greater than 0. We talk about the intervals of the domain when something's happening, like it happens from 0 to 5 or whatever. But we look at the y values. Is the graph positive or negative? That sort of thing. So like we were talking about the parent functions the other day, and we looked at the square root function and pretended like we didn't know anything about it, right? So let's just kind of back up a second. So f of x equals the square root of x. And we're just going to pretend like we have no idea what the function looks like. And but I do know I can't put in a negative, right? And I know I'm not going to get anything negative. So the graph lives in the first quadrant. Now, think about this for just a second before you answer. Even though it all lives in that first quadrant there, is the function always positive? Is there one time when it's not positive? Where would that be? The what? 0. I heard it. 0. Okay, 0. Because the function, remember, it looked like this. And I can figure that out from here because I can substitute in 0. So if I want to say when is it positive, I have two options here. It goes from 0 to infinity, right? So the y values are always positive. Even though I'm talking about the y, it's on the interval from 0 to infinity. You never include infinity. It's always an open interval. Do I include the 0? Is it positive from 0 to infinity, including 0? Is 0 positive? No, it's not positive or negative. So I don't include it. It would have to look like that. So it's positive on the interval from 0 to infinity. I could also say when x is greater than 0, you might see it that way. We are not going to write things in inequality notation because it is just a hot mess when we do it. Interval notation, it's always left to right. This, y'all start making things up. Things are backwards and weird, and we're just not even going to go down that road. Do we need to be able to read it? Yes. That doesn't normally seem to be the problem. It's when you write it when you're like, I don't know what the heck is happening. So then, the function itself is negative when the graph of f, which means the y values, lies below the x-axis, so the outputs are less than 0. So is this function ever negative? No. Okay. So again, we're looking at the y's, we talk about the x's. Everybody okay with that? All right. So multiple representations. This is just kind of a general thing for kind of the course itself. So throughout this course, we'll learn and study concepts utilizing the four mathematical representations: graphical, analytical, numerical, and verbal. So to be successful, we all want to be successful in AP Pre-Calculus. We need to be able to identify important information. It's not about solving the problem as quick as we can and being the first one done. Nobody cares. We don't even want to know if you were done already. I'm still reading the question. From each representation and construct equivalent representations. This comes up a lot. So making it look like they look like two completely, oh my God, back up my words. They look like two completely different things, but they actually represent the same thing. So it might sound scary or confusing at first, but we'll have lots of opportunities to practice, so don't worry. We practice a lot. All right, flip it over. So we've got this vase here. It says the figure shows an empty vase at time t equals 0. We always want to pay attention to any time stuff they give us. The water begins pouring into the vase. So it's empty, it starts to pour into, it's not going out because that would be a different kind of answer, at a constant rate until it's full. Which of the following could depict this situation where time in seconds is the independent variable and the height of the water in the vase in inches is the dependent variable? So I want you to look at it for a second. I'm going to give you a minute or two to discuss it at your table. Even if you can't figure out what the answer is, maybe you can eliminate some for sure. Okay? So discuss. And don't be afraid to speak. At least come up with one or two that you could eliminate. Okay. Got a little quiet, so maybe we're done talking. So let's talk about a couple of things before we jump to the answer here. This constant rate. Do you understand what that means? Keeps going, same rate. Like, I'm on cruise control, right? I'm going 40 miles per hour. I'm on cruise control. My rate is constant. And what's another word for rate or rate of change? Slope. Anytime you see rate or rate of change, it is slope, right? And you've been doing slope forever. Okay? What you haven't been doing is the rate of change of things that aren't linear. So the only slope really you've talked about is of lines, and that is a constant rate of change. Like your slope is 3, it's always 3, right? But I'm on cruise control and I'm going 40 miles per hour. I'm coming up to a stop sign. So I put my foot on the brake and now I'm slowing down. So now my rate of change is changing. You with me? And it's constantly changing because I'm slowing down. Yes? So I'm slowing down. At any given moment, I can take a snapshot and say, oh, that was 37 miles an hour. Oh, 36.9 miles per hour, something like that, right? So we've got an instantaneous rate of change where when I'm on cruise control, it's a constant rate. Okay. So now when we are looking at this vase, it's pouring in at a constant rate, but that's not what our dependent variable is. It's the height. Is the height going to be changing at a constant rate? Yes or no? What do you think? No. What would the vase have to look like for it to change at a constant rate? Give me an example of something. How would the height change at just a constant rate? Like what? Like a cylinder. Beautiful. So here's a very bad cylinder. But if it looked like a cylinder, then the height would change at a constant rate, right? Even think about your bathtub. Your bathtub is it's mostly rectangular, right? I mean, I know it's not exactly, but if we pretended like it was exactly, then the height would change at a constant rate. So this is what the constant rate would look like, which means we know it's not 8. Okay? But the rate is changed. So before we worry about the rest of them, even if you already feel like you know the answer, let's talk about this. Let's just look at right here. If as I'm filling this up, the diameter of the vase is increasing. Would you agree with that? It's getting bigger. All right, so we're going to write over here. I'm going to write some words out. Diameter is increasing. Okay, so I can abbreviate increasing, INC period. Here's one weird thing about the stuff we have to write out. Sometimes we can abbreviate things, and that's beautiful. There are specific things that we can't abbreviate, and they're kind of picky about. Or we think they're going to be kind of picky about, so we're just going to play it safe and actually write stuff out, okay? If we can abbreviate, trust me, we're going to abbreviate, all right? Because I don't want to write it or read it either, but we need to make sure that we're clear about things. All right, then I'm going to do these little dots. Can anybody tell me what those 3 dots mean? What? Oh, increase, that's INC period, it's increasing. You can write out increasing if you want to, but the 3 dots means therefore. Therefore is kind of a long word, so we're going to use the 3 dots, but that's what it means. Okay. And that's a universal thing. It's not something I made up. We don't get to make up abbreviations, all right? All right, so the diameter is increasing. All right, so if the diameter is increasing, the diameter is increasing, therefore the height, now is the height increasing or decreasing? Increasing the whole time, right? Because it's filling up. Height is increasing at what kind of rate? Is the rate that is it the rate the height is increasing? Is the rate increasing or decreasing? It's coming out like this. So if it's getting bigger, is the height of the water going to change faster or slower? Slower. So the height is increasing at a decreasing rate. Some of these words, again, can kind of mess with your brain. I'm going to give you a way to kind of understand this a little bit better, but you have to understand the concept of, okay, that makes sense. Think about actually filling up the water, right? So now let's think about here. Pretend like that's horizontal. Right about here. Now the diameter is the diameter increasing or decreasing? Decreasing. Okay, diameter is decreasing, therefore, is the height increasing or decreasing? Still increasing, good. Height, my handwriting is terrible. I'm sorry, my handwriting is not the best, and this board makes it worse, so if you can't read the stuff, let me know. Diameter is decreasing, therefore, height is still increasing at, what's happening to the rate? Is the rate increasing or decreasing? Increasing is going to go pretty quickly, right? Height is increasing at an increasing rate. So do you understand those words and that concept there? Now, they didn't ask me for the words, but they could. But if I don't understand that on some level, I can't pick this out. Now, because we're pouring water in and the height is always increasing, based on that statement, which other one can I eliminate? C. Because the height increases and then decreases and then increases. That is not what's happening. Okay? So now I'm really just looking at B and D. If I start off at 0, I increase at a decreasing rate. Do you think that's B or D? D, because this one speeds up, right? This starts, then the height is increasing, but the rate is decreasing, and then the rate starts to increase. So our answer is D. I can pretty much guarantee you there'll be at least one base question on the multiple choice part of the test, because that was in all of the practice tests, and I'm pretty sure there was one on the real test as well. So, but that's just kind of a general concept, right? Now we're going to kind of tie all this stuff together. Let's look at this graphical behavior of functions. All right, so as the input values, we have increasing and decreasing, right? As the input values increase, the output values always increase. That means as x gets bigger and bigger and bigger, y is also getting bigger and bigger and bigger. When we are looking at any of this stuff, x is going from left to right, and then we're seeing what's happening with y. My y values are getting bigger, that's what makes it increasing. Here, decreasing, input values increase, output values always decrease. As x gets bigger, the y's are decreasing. That is the function increasing and decreasing. Okay? Then we have concave up and concave down. And that is talking about the rate of change increasing and decreasing, not the function itself. Now, concavity is something that you most likely talked about in science at some point, at least a little bit, probably in junior high. We talked about lenses and stuff, right? So concave up like a cup, like it could hold some water, but at the same time, it doesn't have to actually be able to hold water. By that, I mean sketch things nicely. Like an exponential increase. The left-hand side doesn't actually tilt up, but that would still be concave up. You with me? Water would totally run out, but it is what it is. So we got concave up and concave down. And we have the rate of change increasing for concave up, rate of change increasing, rate of change decreasing for concave down. So that means I could have looked up here and go, oh, look, it's concave down. That's why the rate of change is decreasing. Now, like I said, when I'm putting my foot on the brake and I can take a snapshot at 36.5 miles an hour or whatever, actually finding that mathematically you can't do without calculus. So if I wanted to know what is the rate of change right here at this point, we're not going to have the skills this year to figure that out, but that's okay. We can estimate it by getting really, really close. Like I can pick 2 points on either side of it, because I can find slope with 2 points, find the slope of the line that goes through there, and then that would be a pretty good estimate for my little purple point. You agree with that? Okay, so we have 2 different types of lines that we can draw on here. I'm going to kind of say the words today, but we'll talk about them a little bit more on Monday. Tangent lines and secant lines, you talk about them a little bit in geometry. But just kind of like I said, I'm going to use it and say it right now. We'll talk about it more on Monday. But if a tangent line is going to touch it like just at that purple point. And I'm probably not going to do a great job of drawing it because of the pen. And even on your paper, it might not be perfect. It's okay. We're just going to get them so that kind of looks sort of tangent. We can pretend a little bit. So I'm going to draw a few tangent lines along the way saying like, I would really like to know what these 5 are. See, I missed a few, but that's okay. It's close enough. It's parallel, so it'll be fun. This slope, when I start right here, you can see my pen, is this slope positive or negative? Negative. And as x gets bigger, the slope is heading towards 0, and then it's getting bigger, so then it's getting positive. So my slopes, my literal slopes, are increasing. Does that make sense to you? Then here, this is positive, it's heading to 0, and then it decreases. So my slopes are literally decreasing the entire time. I will tell you, I'm very honest and transparent with you. At the beginning of the year last year, we started talking about this stuff. I thought it was going well. And then I realized most people, that just blew their minds. What students have the most trouble with is separating the fact I'm talking about the function or I'm talking about the rate of change. And you have to separate that in your brain or you get all mixed up. Also, this whole line thing was a little wacky, okay? And so I'm telling you that because even after I gave them a way to get through it, they were still obsessing over it. So it might take a minute for it to really start to make sense, especially when we start working questions, but that's okay. We have something that's going to help us, and maybe I didn't introduce this soon enough last year, called the fun chart. So write a little lowercase f for my function. Okay? Then my function can be concave up, concave down, increasing, or decreasing. Do you see why it's called the fun chart? So it kind of looks like the word fun, but it's not an actual U and an N, which I did see some students writing at some point. The next row is capital R for rate of change. My rate of change can be increasing or decreasing or positive or negative. Right? You're going to write this little fun chart a lot. So much so that you won't write it wrong. It'll be fine. It's pretty easy to write down. But let me show you how this is going to help you. You see this right here? This is concave down. So my rate, since it is concave down, my rate of change is decreasing. This is concave up, my rate of change is increasing. Is the rate of change for this function always positive, always negative, or a mixture? What do you think? Is the function increasing the entire time? The function is increasing the entire time, therefore the rate of change is positive. You see how that works? So you don't have to overthink it and get confused with the graph, okay? And we will use that a whole lot more. One of the things I wanted to do today, but we're not going to have enough time, is I have this printed out for you. We're going to tape it in our ISN. That's why I had on here that it was going on 2 pages. We'll have to do that on Monday. That's fine. So just don't lose your notes, because we're not 100% done. And there's other pages that go with it. And that'll be it. You don't have an assignment today. If you need to work on your summer assignment, do that. If you are new and didn't know about it, if you're not brand new, then don't tell me you didn't know, because it makes my head want to explode. It's on the school website under academics, and then it's down there somewhere. But remember, the instructions are wrong, and I did not change them yet. It says to create one with your district account. Do not do that. Make it your personal account. If you got through the whole thing,